Alright, let's see how we can make a 3D terrain, which would sometimes be useful for games or other programs. And here's the terrain that we're going to create in this lesson. Now the question is, how do we represent a terrain? The easiest approach would be to have a grid in the XZ plane, and for each point on the grid to specify the height of the terrain at that particular point. And this turns out to be a pretty good idea, actually. We can't represent every terrain. For example, we can't have a wall that's directly vertical or a wall that's going backwards. But still, we can represent quite a bit. Now we could take all of these heights and put them directly into our source code, just hard code them into the program, but it would be better to have an external file that stores all of the heights. And one approach that we could use is to use an image file and have each pixel in the image represent a particular height. So it'll be a grayscale image file, and the color white will represent the highest possible terrain, the color black will represent the lowest possible terrain, and gray will represent just heights in between those two heights. And this also turns out to be a good idea. That particular image file would be called a height map. One word, height map. And there are tools online for editing and making height maps, although I haven't really looked into it too much, so you can do that on your own if you want. For this particular program, we have this file right here, which is our height map. Let's take a look at it. I'll just zoom in a little bit. And this is what the height map looks like. Actually, one advantage of a height map is just by looking at this picture, you can get an idea of what the terrain is supposed to be like. So you can see that there are mounds right here and right here, which is one advantage of height maps. So that's what we're using for this program. Now let's take a look at the code for the program. We have at the top a terrain class, which, you guessed it, represents the terrain. And the terrain class has a few fields. It has a width and a length, which are the number of grid points in the X and the Z directions. Then we have a two-dimensional array, h's, which stores the height of the terrain at each particular grid point. Then we have a two-dimensional array normals, which is going to store the normals at each particular point. And each normal is a vec3f object. Vec3f is a class that I wrote. It's a vector of 3 floating point values, and it uses this right here, include vec3f.h. So let's take a look at the header file right here. And vec3f objects do basically everything you would expect vectors to do. So you can multiply, divide, add, and subtract using star, slash, plus, and minus. You can access individual elements of a vec3f object using brackets. So if you have a vector called vec, and you want to access either get or set the first element, you would use vec open bracket 0 close bracket. For the second element, it would be vec open bracket 1 close bracket, and for the third element, it's vec open bracket 2 close bracket. If you want to construct a vec3f object, you use this constructor right here. You just pass in the 3 values for the different elements in the vector, and you'll construct a vec3f object. And let me scroll down. There are a few other methods. We have a method to normalize to return a normalized version of a vec3f object, or to take the cross product of 2 3-dimensional vectors. And we can actually also see out vec3f objects, which is cool. And that's the idea behind the vec3f class. That's what our normals are going to be, vec3f objects. After that, we have the computed normals field, which is going to... Well, so basically, what we're going to do is we're going to set all of the heights of the terrain individually, and once we're done setting all of the heights, we're going to compute all of the normals. And this will keep track of whether we've computed the normals yet. Before we compute the normals, all of these normals will just be garbage, whatever happens to be in memory at the time. So we're going to want to keep track of whether we've already computed the normals yet. Then we have the constructor, which constructs the two-dimensional arrays that we're going to need. And we have a destructor, which just deletes the two-dimensional arrays right here. We have a width and a length function, which return the width and the length of the terrain. We have setHeight and getHeight functions, which set and get the height of the terrain at particular grid points. And we have a compute normals function which computes all of the normals for the terrain. And I'm going to skip this for the time being. We're going to come back to it. So that's the function for computing normals. We have a getNormal function which returns the normal at a particular grid point. And that's our terrain class. After that is a function called loadTerrain, which just takes a height map, or a file name for a height map, and it loads it into a terrain object. So what it does is it calls loadBMP to load it into an image object, and then we construct a new terrain using the width and the height of the image, and we go through all the pixels in the image and set the heights appropriately. So what we're going to do is, for each pixel, we're going to take the red component of the pixel, right here, which actually we could take the green or the blue components just if we wanted to. It doesn't really matter, since this is a grayscale image. And these components will range from 0 to 255. We're just going to do a little arithmetic right here to make it so that they're between negative height over 2 and height over 2, using the height parameter up here. And then we call setHeight. And once we're done, we delete the image object, which we don't need anymore. We call compute normals, and we return the terrain that we've just created. Then we have some variables. We have our cleanup function, which just deletes the terrain. And we call this cleanup function when the user presses escape. Then we have, in the draw scene function, we have some standard lighting and translating and scaling stuff that we've already seen. We've already seen how all that scaling and translating works before. Then over here we're actually going to draw the terrain. And we're going to use triangle strips, GL triangle strip, which is new. And what a triangle strip is it tells OpenGL to draw a triangle between every 3 consecutive vertices before the next call to GL end. So if we were to specify 5 vertices between this call to GL begin, GL triangle strip, and this call to GL end, what OpenGL would do is it would draw a triangle connecting the first, second, and third vertices. It would draw a triangle connecting the second, third, and fourth vertices, and a triangle connecting the third, fourth, and fifth vertices. And we're going to be using triangle strips to draw the terrain. Actually, let me show you a picture that illustrates how we're going to draw the terrain. And this is an animated picture of a really small terrain that's just 3 grid points by 3 grid points. And this sort of gives us an idea of how we're going to draw triangle strips. We're going to draw from here to here to here to here to here to here, and we're going to get each row of the terrain using one triangle strip in this particular manner. So that's how this code over here works, basically. It just draws triangle strips like that. And you'll notice right here that we're dividing up each of the grid cells from the lower left to the top right, or I should say from out and to the left to in and to the right. And we could have divided the grid cells up the other way, from in and to the left to out and to the right. Although it shouldn't really matter too much if the terrain is sufficiently smooth. The terrain will look about the same regardless of the way that we divide up the grid cells. Another thing we could have done is we could have used GL triangles to draw the same set of triangles that we're drawing using GL triangle strip. But actually this would be slower, because we'd have to specify more vertices. And that means we'd have to send more data to the graphics card. So using GL triangles would be slower than GL triangle strip. Another thing we could have done is use GL quads to draw each of the grid cells individually. And we actually don't want to do this because the 4 points on the grid cell aren't necessarily in the same plane. So we want to stay away from GL quads. And that's how we draw the terrain. Down in the main function is where we actually call load terrain and load in the height map into this terrain variable. And that's it. Actually, I skipped over the compute normals function, so let me go back to that. Let me just close that image and go back up to compute normals. So here it is. First of all, if we've already computed the normals, we don't have to do anything, so we'll just return from the function. And we're actually going to make a 2-dimensional array called normals2, which is going to store sort of an intermediate approximation of all of the normals that we're going to use to figure out the actual normals. And the question is, how do we determine the normal at each particular point on the terrain? One way we might think to approximate one of these normals is to take a triangle connecting a particular point, the point to the left of it, and the point immediately outward from it, and just use that triangle and take a vector that's perpendicular to that triangle. That'll give us an approximation of the normal at the point. And we could actually use any of 4 adjacent triangles to get a potential normal vector, to get an approximation of the normal vector. And what we're going to do is just average together the normal vectors for all of these 4 triangles. And what does it mean to take an average of normal vectors like this? What does it mean geometrically? It actually doesn't mean anything. It's just a way I came up with to make the normals look good. And that's the cardinal rule of computer graphics: do what looks good. So we're just going to try this and see if everything looks good in the end. So here's our code. We loop through all of the points, and we're going to use this sum variable to help us figure out the average of these 4 normal vectors. We compute 4 vectors out in left and right, which are going to store vectors. This out vector will store the vector from the point to the point immediately outward. This in vector will be the vector from the point to the point immediately inward from it, and so on for left and right. So we just compute these 4 vectors because we're going to use them to figure out the normals for the triangles. And by the way, you'll notice, for example, if we're on the left edge of the terrain, then we're not computing the vector left because there actually is no point to the left of the point. There's no such vector as left, so we're just not going to compute it. And then we're going to compute the individual normals for the 4 adjacent triangles. And we're going to do that using the cross product. So, for example, right here, we have the triangle that contains the point immediately to the left of it, and the point immediately outward. And 2 of the edges of that triangle are this out vector and the left vector. And in order to find a vector that's perpendicular to 2 other vectors, you just take the cross product of the vectors, which is what we're doing right here. So this right here gives us a vector that's perpendicular to that particular adjacent triangle. And we're just going to take it and add it into this sum variable. So we're going to add together normal vectors for all of the adjacent triangles, and then store it into the normals 2-dimensional array. And by the way, we're just using the sum instead of the average, but this is a normal vector, so all we really care about is the direction. The magnitude of the vector doesn't really matter, so the sum is pretty much the same thing as average. It really has the same meaning. Now, after that, we could just use this normals 2 vector directly to be our normals, but actually, if you do that, which you can do by changing this variable to changing this constant to be 0, which you'll see why that'll just use these vectors directly in a moment. You'll see why that is. So if you do that, actually the terrain will look kind of rough. The lighting on the terrain will look pretty rough. And that's because if we do things that way, then all the normals are too localized. They depend too much on points that are too nearby. And actually, for the height map, I only have 64 different heights for the individual points on the height on the terrain. And what that does is it basically doesn't give us too much precision in defining all of the heights of, on the terrain. So the effect of that is, if we were to use these normals directly, things would look kind of rough, kind of ugly looking. So we're actually going to smooth out the normals a little bit, and the way we'll do that is we'll just take each of the points and we'll average together the normal at the point and some of the adjacent normals, some of these approximated normals that we've used, that we've computed. And we'll do that right here in this loop. We'll just basically take a weighted average of the normal at the given point and the normal at the adjacent points. And the weight for the normal at the adjacent points is fallout ratio, this constant right here. The weight for the normal at the point itself is just 1. So here we go, we're just adding together all of these, producing a weighted average. And one thing we're doing right here is we're making sure that the magnitude of this normal vector is not 0. Because if we use the 0 vector for a normal, that doesn't really make any sense, because that vector doesn't have any direction. It's not really a normal vector. We can't really use it. So in the unlikely event that our vector turns out to be the 0 vector, we're just going to set the average vector to be this arbitrary vector right here. And then we'll set the normal, we'll set the particular element of the two-dimensional normals array to be this normal vector that we've just computed. And that'll give us good-looking normals for our terrain. And after we're done with that, we just delete this normals2 two-dimensional array, which we don't need anymore. And we set computed normals to true. And that's how we can compute some normals. And that should give you an idea of how we can do 3D terrain in OpenGL.